Alright, so we're going to be talking about matrices. First of all, for matrix transformations, there's no easy way about this. You're just going to have to memorize these. You pre-multiply the transformation matrices. That's because matrix, you can't use cumulative multiplication with these. Order does matter. But so memorize these, and you can see what kind of transformation is going to be accomplished. So let's go over matrix addition, subtraction, and multiplication. For matrix addition, it's pretty self-explanatory, and the same rule is applied for subtraction. You just change the sign here. But wherever the placeholder is in the first matrix, that's where you're adding or subtracting in the second one. So A is in row 1, column 1, G is in row 1, column 1, so those two get added together in the result, and so forth. Also, when you talk about the location within the matrices, we can also refer to it as subscript row, subscript column. So if you have A11, that would refer to row 1, column 1. Next, multiplication. This is a little bit more difficult to wrap your head around. What you're doing is you're multiplying the first row by each column, and that will create your top row in your resulting matrices, or your resulting matrix. So A times G, B times I, and C times K. That's one new term, or that's the first new term in your resulting matrix. Then you do, for column 2, A times H, B times I, or I'm sorry, that's J, B times J, C times L, and that will create the second term in your top row of your resulting matrix. Now that we've multiplied the top row by each column, we move on to row 2. And likewise, we're working on row 2 now of the resulting matrix. And you apply the same rule. Each row item times every row in the column. So D times G, E times I, F times K. That's our first term on the second row, column 1. And then we do D times H, E times J, F times L, and that will be our last remaining term. And I've described that verbally right here, but it's a little bit more complicated when you're reading it. Note when you're multiplying matrices, the number of columns in matrix 1 must match the number of rows in matrix 2. So this is a big part of why matrix multiplication is not commutative, yeah. So order does matter, and you can see why based on how we just multiplied these through. It would not work if we multiplied this matrix first, or pre-multiplied this matrix by this one, is I guess the correct terminology. Alright, for the determinant of a matrix, this does not stand for absolute value, it just stands for determinant. So note that. But if we're going to take the determinant of matrix A, we would do AD minus BC. For a 3 by 3 matrix, and this matrix, just to give you an idea, is A, B, C over D, F, G, H, I. So that's what this matrix looked like. So you do the first term times E, F, H, I, B times D, I, D, F, G, I, and then C times D, E, G, H. So A by the lower right, 4, B by the outside items, and C by the lower left. That's how that's operating. And note the sign. So you go positive, negative, positive, and then for bigger matrices than this, you would continue that pattern of positive, negative, positive, negative, positive, negative. So when we multiply these out, because we need to come up with a result, we take the determinant of this 2 by 2. So we use the same logic as we had here. So it would be, for example, in this first one, it would be EI minus FH. And you'll note that that's the same thing as here. So AD, EI, BC, FH. And then you multiply A by that, and you would get a resulting number. By the way, note that if a matrix, that if any matrix has a determinant that is 0, there is no inverse, so you don't need to go any further. If they ask you to find a inverse of a matrix, or they may ask you, why there is or is not, and you may not even have to calculate it. So go ahead and get rid of these. To find the inverse of a 2 by 2 matrix, they are not going to ask you. I've never heard of anyone being asked to do the inverse of a 3 by 3, so we're only going to learn how to do a 2 by 2. So in this matrix here, they're asking for the inverse. Again, when we talk about inverses, this is not a power. That's just the notation. We multiply by 1 over the determinant A, and that's why, if the determinant is 0, there is no inverse, because dividing by 0 is impossible. And then you flip-flop D and A, so they change places, and B and C become negative. So if you multiply all that out, you will get an inverse matrix of A as your result. So 1 over the determinant, which we found in the previous section here. Flip A and D and make B and C negative. You can also represent geometric shapes as matrices. So we talked about the transformations at the beginning of the video. Triangle is by far the most common on the praxis. So to represent a triangle as an example, if one point was at x1, y1, another point was x2, y2, the third point on the triangle is x3, y3. So we're talking about the corners here. This can be represented in a matrix like this. So you would pre-multiply this matrix by the transformations we have here, and that would result in the transformation requested. And we'll move on next video.